This is the B-1B Lancer, a variable sweep strategic bomber engineered for sustained supersonic penetration at low altitude. With a maximum takeoff weight exceeding 216,000 kilograms, every structural decision on this aircraft is dictated by stress, heat, and fatigue limits. The Gunship Gray coating is not cosmetic. It reduces visual contrast, manages thermal radiation, and supports radar signature control. At the core of the airframe lies a semi-monocoque fuselage, distributing aerodynamic loads across frames, stringers, and reinforced skins. Internal volume is maximized to house fuel, avionics, and 3 weapons bays without external hardpoints. The variable sweep wing is the defining feature of the B-1B's aerodynamic envelope. Wing sweep ranges from 15 degrees for takeoff to 67.5 degrees for high-speed dash. This geometry allows the lift-to-drag ratio to remain optimal across Mach regimes, from 0.2 to 1.25. Sweep motion is driven by a centralized wing sweep gearbox synchronized across both wings. Torque loads during sweep exceed hundreds of kilonewton meters, requiring titanium pivot fittings. Each wing houses multi-spar structures designed to survive terrain following flight at under 200 feet AGL. Flaps and slats increase effective wing area during low-speed phases. Control surfaces are fly-by-wire augmented, filtered through quadruplex redundancy. Every control input is mathematically damped to prevent pilot-induced oscillation. At the heart of propulsion are 4 General Electric F101, GE102 turbofan engines. Each engine produces approximately 30,000 pounds of thrust with afterburner engaged. The low bypass ratio balances fuel efficiency with supersonic thrust requirements. Air enters through variable geometry intakes designed to manage shock waves at high Mach. These intakes decelerate supersonic airflow to subsonic speeds before compression. Compressor stages raise air pressure by a factor exceeding 20 to 1. Fuel injection occurs in an annular combustor operating at temperatures over 1,600 Kelvin. Turbine blades are single crystal alloys cooled internally by bleed air. Afterburner ignition increases thrust by injecting raw fuel into exhaust flow. This mode is used sparingly due to exponential fuel consumption. Total internal fuel capacity exceeds 120,000 pounds. Fuel tanks are integrated into the fuselage and wings to reduce structural redundancy. Fuel transfer is computer controlled to maintain center of gravity limits. Even a 1% CG shift at Mach 1 dramatically alters pitch stability. The B-1B's landing gear is designed for extreme weight absorption. Each main gear strut absorbs vertical loads exceeding 250,000 newtons on landing. Carbon brakes dissipate kinetic energy through heat conversion. Brake temperatures can exceed 1,000 degrees Celsius after maximum weight landing. The cockpit is optimized for crew workload management during long missions. 4 crew members operate within a pressurized, shock-isolated capsule. Glass cockpit displays integrate flight, navigation, and weapons data. Terrain-following radar is a defining survivability system. It scans terrain ahead, computing vertical clearance in real time. Autopilot commands pitch adjustments at rates exceeding human reaction speed. At 540 knots, the aircraft travels 278 meters every second. Manual terrain following at that speed is mathematically impossible. Defensive avionics include radar warning receivers and electronic countermeasures. Threat libraries are updated continuously based on intelligence inputs. Chaff and flare systems deploy within milliseconds of detection. Electronic warfare is calculated warfare signal strength versus distance squared. 3 internal weapons bays preserve aerodynamic cleanliness. Rotary launchers distribute payload mass evenly. Maximum internal payload exceeds 75,000 pounds. Weapon separation timing is synchronized to airflow dynamics. Incorrect timing risks recontact with the airframe. Release solutions are computed using ballistic and aerodynamic models. The B-1B no longer carries nuclear weapons under current treaties. Its mission focus is now conventional deep strike dominance. At high speed, structural heating becomes a limiting factor. Skin temperatures can exceed 120 degrees Celsius during sustained dash. Thermal expansion is accounted for in panel tolerances. Structural fatigue life is tracked using cumulative damage models. Every flight hour consumes a fraction of design life. Maintenance inspections target high-stress nodes first. Modular systems reduce downtime between sorties. Redundancy is not optional. It is survival mathematics. Electrical power is generated by engine-driven generators. Total onboard electrical demand rivals that of a small town. Power distribution is isolated to prevent cascade failure. Hydraulic systems operate at pressures above 4,000 pounds per square inches. They actuate flight controls, landing gear, and bay doors. Triple redundant hydraulics ensure continued control after damage. Environmental systems regulate temperature and pressure at altitude. At 40,000 feet, ambient pressure is less than 1/4 of sea level. Life support is entirely machine regulated. Human limits define cockpit constraints. During takeoff, wings are forward swept for maximum lift. Rotation speed varies with weight, density, altitude, and runway length. Once airborne, sweep begins as drag reduction becomes priority. Climb profile balances fuel efficiency and mission timing. Cruise altitude optimizes specific fuel consumption. Ingress phase begins at terrain masking altitude. Radar horizon is reduced by Earth curvature. At low level, survivability increases exponentially. Egress relies on speed, not stealth alone. Acceleration margins are preserved for escape. On return, fuel is redistributed for landing stability. Approach configuration restores maximum lift geometry. Descent rate is tightly controlled to prevent structural stress. Touchdown energy is absorbed mechanically, not electronically. After landing, engine cooldown prevents thermal shock. Post-flight diagnostics log thousands of parameters. Every anomaly is data-driven, not anecdotal. The B-1B is not a single machine, it is a system of systems. Each subsystem exists to support the mission profile. Speed, range, payload, survivability, each balanced mathematically. The Lancer was never designed for simplicity. It was designed for dominance in contested airspace. Engineering decisions reflect Cold War survivability logic, yet its relevance persists through continuous modernization. The airframe is a compromise between physics and strategy. Every rivet carries a load calculation. Every system answers a threat scenario. This is not just an aircraft. It is a flying equation of power projection. And this is how the B-1B Lancer works.